This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. In today's topic, we will see the general formulation of a finite volume numerical scheme. So, in the previous session, we have seen what is the difference between finite volume method and finite difference method. So, in the previous 4 modules, whatever we have discussed was majorly involving with finite difference method. So, first unit it was about the introduction, so where we have seen the governing equations, and we have seen the types of control volume, and we have seen the shock fitting and shock capturing approaches, and we have seen the explicit method, implicit methods in the third module, and partial differential equations and their classification and CFD techniques. So these things in general we have seen. So the fifth module is about actually the finite volume method, where the scheme or the type of the discretized equation which we use is very different. It's like different from the finite difference method. So we'll just see small recap of what is finite difference, finite volume, and then we'll go for the formulation. So here you can see, so we have a cell. So here you can see this is a cell. What here we have the grid points. So the combination, the intersection between two grid lines. So X grid line, your Y grid line. So intersection between two grid lines, like we will get a grid point. Okay. So in the finite difference method, we solve the governing equations at these grid points. So at these locations. Okay. So at these locations. Whereas in the finite volume method, so what do we have? So we will be solving at the center of the cell. Okay. So we have to mark, or we need to find out the center of the cell, and then we will calculate those values at the center of the cell. So that is what we have finite volume method, and we have seen two different approaches where initially you have the grid or the mesh of the cell. So first the cell or grid or mesh is drawn, then we will mark the centroid based on the neighboring edges. Let's say we have this edge 1, this is edge 2, edge 3, edge 4. So we will have to mark what are the midpoints of these edges. Let's say these are the midpoints of these edges. And when you join this all midpoints, so you'll get an intersection point where that is called the center of the cell. Therefore, this center of the cell is the point where we solve the governing equations in terms of finite volume. So this is one way. The other way, so we define point once, or let's say we define the center of the cell, and then we construct, let's say, the cell around it. This is one kind of approach. Okay, so we'll construct a control volume. So based on the points which are available, and such that these points are at the center of the cell. So these are the two different approaches which are available for the finite volume method. But so we'll go with this where the grid points are like the mesh or the cell is defined. Then we will mark or we'll calculate what is the center of the cell. So this is the approach, right? So when you compare actually the difference between the finite volume method and finite difference method, so we have seen that finite difference method is applicable for structured, let's say, structured mesh entity, and then for simple problems, not like complex problems. It's a simple problem. So for the curved entity, applying finite difference method is somewhat hectic task. So let's say simple geometry in the sense, let's say you have this square where you have the flat plate here. So this is your flat plate. So we'll take this as wall. Okay. So here you have left boundary, here you have right boundary, here you have top. Okay, and this bottom. Fine. So here you will calculate the solution using FDE method, which is finite difference method. Because this is very straightforward, and here you can mark the location of the grid points properly, and you can do the index, let's say, or let's say the arrangement, so the neighboring points arrangement or the grids arrangement, they are uniform and more or less complicated. So when you go for the complex geometry or the geometry which has curved nature or the geometry which is having the intersections, so they are like more like that. So let's say we have airfoil. So we have an airfoil. Sorry. So we have an airfoil. For the airfoil, we have other airfoil. Let's say. So this is the entity. So we have some attachment here, but we are the linkage is the this is the flap. This is the wing. So here, what is happening? So if you want to perform the CFD analysis over this entity, so let's say this entity, whatever we have, so it's a hectic task for finite difference method. Why? So you have the curve nature and you have some intersection, and you have two different airfoils, or let's say two different shaped airfoils, or it's size airfoils which are attached together. So during intersection here also the mesh has to be performed, and that would give hectic task. So people use combination of structured and unstructured mesh such that places where it is simple, they use structured mesh. Places where they are complicated in sense, let's say you have the intersection here at this intersection, or the curved nature. So at those locations, we use the unstructured mesh. Fine. Now, when we use unstructured mesh, so solving the grid points with the finite difference method is hectic. So proper arrangement of grid points is not shown clearly, and whatever the neighboring points are there, it is surrounded by we have, if you see point of interest, it is surrounded by so many neighboring points, and the matrix size will be very high. So these things are there. Okay. Now, when we go for the finite volume method, since we are solving at the center of this cell, so we do the interpolation between the edges, and then we will actually get the center. There we will calculate whatever the values we calculate the cell faces, or let's say at the edges, so we will interpolate at the center. Okay, so this is what we do in the finite volume method. So this is very different. And one important thing is that here in the finite difference method, so we have a residue actually. I think we have seen that is called the truncation error. Fine. The truncation error, so whatever we have, so that leads to unstable nature if the error accumulates as the simulation progress with the time. Okay. So as the simulation progress with the time, so the truncation error keeps on increasing actually. So the error gets accumulated, and it leads to oscillatory and unstable solution. Okay, so these are the disadvantages of the finite difference method. So whereas finite volume method, what do we have? So we have the conservativeness. Conservativeness. So whatever flow go here, it will come back here, or let's say, so the internal fluxes will get nullified. Okay, so global conservativeness will be there. So whatever thing we send here, so this thing will come out like without any like residue kind of thing. Right. So this is how, and this is why it is very flexible with working with finite volume method. The mathematics maybe will be somewhat complex compared to the finite difference method, but finite volume method is applicable for all types of geometry, all scenarios, all locations. Okay, so that's why this has its added advantage. Fine. So that's why we apply it for complex geometries. Right. So here you can see the integral form of governing equation. So this is the generalized equation actually. Okay. So this is the this is the term which is called flux term. So here you have density, area, so velocity. So basically m dot, so which is the flux leaving per unit area. Okay, so that thing is there, and here you have the diffusion term actually. So this is the diffusion term. So any generalized equation you take, so it considers the convection term. So this is called convection term, and this is called the diffusion term, and this one is called the source term. Okay, so this is called source term. So this is what the convection term, and this is the diffusion term, and this one is the source term. Okay, so these three things are available. So at all applications. Let us say example. So when you take an example of let's say flow going through a channel, so it depends. If you have low velocity, so it will be diffusing everywhere. So yeah, it is diffusive nature actually, and it will move it. So what happens? It has both the diffusion nature and the convection nature. So the meaning of source term is like if you have any source which is evaluated within the model itself, so that let's say heat transfer or let's say flow propagating through the point. So these kind are called the sources. Fine. So you have the convection term, you have the diffusion term, and you have the source term. Now, when we are doing the finite volume formulation, what happens? So we have to take the convection term separately. You have to consider diffusion term separately, and any one of them you can club with the source term. So you can take combined the source term and diffusion term, and we can take separately and do the finite volume formulation for the convection term. Why? Because so whatever the numerical scheme we apply for the diffusion term, so this diffusion term is not applicable for the convection. Why? Because the behavior of the diffusion is way different to the convection. Okay, so that's why we have to perform or we have to do the finite volume mission separately, and we will join together. First, we will see what is the finite volume formulation for the diffusion term. Then we will see the convection term, and then we will club together and get the formulation for 1D, 2D, and 3D element. So basically, what is 1D element? So already we have seen. So 1D is nothing but so where the length. So if you take a rod, so this is length L, which is greater than diameter. Okay, so the length of the rod or beam or any kind of thing, so it will be very greater than the diameter of the entity. So therefore this is considered as 1D actually. So this is taken as 2D, where along z direction the dimension is negligible, and along y and x axis you have a significant amount of change in dimensions. And already we have seen the flow variables. Let's say you have pressure. So if it is like p only x, so basically this is called 1D. And similarly you have p x comma y, so we can take it as 2D. So if it is p x comma y comma z, we can take it as 3D. Okay, this is what. So here let us do the finite volume formulation for 1D element. So we are considering only 1D. Okay. So let us see the notation. So here we are seeing point of interest P. So this is the point of interest P. Fine. So this is called the west node. This is called the west node. Okay. And this is called east node. This is called east node. So this indexion or the index notation is not like mandatory fixed. It has to be west or east. It depends. You can take this as left. You can take it as right. It depends on the user, or let's say people who are using this technique. They can write anything, but it has to be conventionally named. That's why people have taken it as west and east. Okay, so P is nothing but the point of interest where we need to calculate the value of the particular flow variable. So when we solve using finite volume formulation, we'll get the values. Right? So let us see the basic index notation and the what are the values of delta PA, PW, PE. So this. So the distance between this point and the west face, the distance between this point and the west face, here you can see this as delta x p small w. So this index notation is very important, and this dimension is very important. Why? Because when we do the finite volume formulation, so we will follow or we will use these notations. Okay, we will use this notation. That is why these are initially taught. Okay, now here we are seeing delta x capital P W subscript. So this indicates the distance between the point of interest P and the west face. Fine. Next, we have delta x PE, capital P small e. So which is distance between this point of interest P and this surface E. Okay. So whatever this element you are seeing, so this is basically the 1D element. So the length is greater than the diameter. Fine. Or the height you can take. So for 1D, length will be greater than diameter, or let's say height or diameter. You can say in this way. So fine. So this is what we have. This is the condition. Next, so we are seeing the distance between the point of interest P and the west node. So which is delta x P capital W. Fine. Similarly, you have P delta x capital P capital E. Fine. So here you can see that with respect to phase, we are seeing west node, which is small w. With respect to east phase, E, we are seeing with the small letter. Fine. So when we are looking at the points, then we are taking the letters as capital. So here you can see the point of interest P, which is capital. East node, it is capital, and east node, it is capital. So if we draw one more point, that will be east. So many points. So if you draw one more point here, that will be west. Okay. So these are the points. Fine. So here, since we are dealing with the 1D, so the dependency of solution at point P is on west node and east node. Okay. So when we derive the formulation, let's say what we have. So we have the surface integral of n dot gamma. So n dot gamma grade phi dA. Dot gamma grade phi dA. So this thing we will see actually. So here you have the surface integral. So how do we change the value of the flux, or let's say the value, or how do we differentiate with respect to these two parameters? So let's say we need this one, and we need this one. Okay. So we know, let's say the values at W. Okay. Or we want the values at W. So how do we calculate? We will see. Fine. Next we can see. So this in general, so basically in general, so NS equation. So what is NS equation? So it is Navier-Stokes equation. Navier-Stokes equation are called the momentum equation. So we have X, we have Y, we have Z. So if you take 3D, we have X momentum equation, we have Y momentum equation, we have Z momentum equation. But when you see the generalized equation, so which is of neglecting the unsteady terms, convection terms, so only the diffusion equation can be obtained. So if you see here clearly, so here this we have convection. So plus you will have some unsteady term, let's say. Okay, so you have unsteady term, you have convection term, diffusion term, source term, pressure gradient term will be there. So this forms the general entity of Navier-Stokes equation. So if you have along x direction, so basically it is called x momentum equation. If you have along y direction, it is called y momentum equation. If you have z direction, it's called z momentum equation. Fine. Now, so what we are saying? So first initially we are seeing the diffusion equation plus the source term. So this is what we have. So this dive. So basically this is called the divergence. Dot grad gamma. So basically this is gamma. Grad phi is d phi by let's say dx. So this is what we have for the 1D. So why? Because since it is 1D, so grad phi is nothing but you will differentiate this term. So we will just see what is grad phi. So grad phi is equal to grad phi is equal to, so we have dou by dou x of phi, so I cap, plus dou by dou y of phi to j cap, plus dou by dou z of phi to k cap. So this is what we have for the grad phi. Fine. So here, whatever dou phi by dou x is there, dou phi by dou y, dou phi dou z, this is coming. So basically the gradient is nothing but, grad is nothing but, g is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. So simply when we write grad phi, so this phi term will get here, will be here, will be here. So this is what we have here. Fine. So this S of phi is S of phi. Basically, this S of phi is nothing but what? So this is the source term. So the source term will be combination of linear and non-linear term. Fine. So if you take phi, that will be any. So here the phi is nothing but what? So it can be any flow variable. So it can be temperature, it can be pressure, it can be velocity, it can be density. So any flow variable can go into this actually. And gamma, so basically this is called gamma. So this is called diffusion coefficient. Now you can see the control volume integration which results. So here we have some change. Basically you can convert surface integral to volume integral. So here you can see this is the surface integral which we have. So this can be converted to volume integral which we have here. So this is called the volume integral. Fine. So n dot gamma grad phi dA. So basically this is called the surface integral. So we have dive gamma grad phi dV. So this is called volume integral. So using Gauss theorem, so we are converting the surface integral to volume integral actually. So this feasibility is there. So that's why we are doing this. And however, you have so control volume of basically source term which is volume integral. So this is same exactly. Fine. So this is what we have done. Now when we take, so let's say d by dx of gamma and d by dx of let's say phi. Okay. So we have let's say integral dA, or let's say equal to 0. So we have this, let's say. So we do actually the integration. So how do we do integration? So we get, so let's say in between, so in between what, let's say in between point P and point W. So what do we get? So if you are doing in between point P and or let's say we have W2 to P. Next, so this is what we have. Another thing, so we have P to E, let's say d by dx of gamma d phi by dx to a is equal to 0. 0. So it is between W to P and it is between P to E. Okay, fine. This is what we have. So when we integrate, what happens actually? Fine. So this will be phi of d phi by dx. So since the area is constant, so for 1D, the area is not changing; it's constant actually. So there is no variation. So therefore, the areas will be same. Let's say if you have 2D, what happens? Let's say you have different area. So we will write this one as A1, this will be A2. Fine. Since we are dealing with 1D, the area is constant, therefore we write A. So this will be gamma phi A into, so P minus gamma A d phi by dx of W equal to 0. So this is what we get. Okay. So gamma A into d phi by dx into P minus gamma A d phi by dx of W. Okay. So this is at the point of interest P. This is at the west node W. Fine. So let us take one thing. So which we have gamma A d phi by dx of P. Okay. So this is what we have. Now, what is gamma P actually? Okay. So how do we get actually? So this is very, very important. Fine. So how do we get gamma P? How do we get gamma W? Is very important. So we have the diffusion term at the faces actually here. So therefore, what happens? So we have to add the P plus W. So gamma P plus gamma W by 2. So this will be at the west face. Next, we have gamma P plus gamma E by 2. So which we get on east face. Fine. So let's see here. So let's say if you want gamma, the east face, this will be gamma P plus gamma W by 2. Sorry, E. These are the east face. Similarly, gamma small w if you want. So basically these are faces. This is west face and this is east face. So for the west face, what is happening? So here, so this is a point of interest P. Here this is west node. Here this is east node. Okay. So what is the value here? So that will be gamma of P plus gamma of W by 2. Okay. So this is the value here and this value is here. Fine. So this is what we have. So when we calculate the gamma, so we have this. Next, what will be d phi by dx? So if it is between these 2 points, that will be phi of P minus phi of W. Okay. So phi of P minus phi of W. Next, if it is at east face, so this is, so let's say we have so d phi by dx. So this can be written as phi of P minus phi of W divided by delta x. Fine. So this for the west face. Similarly, so for the east face, so d phi by dx can be written as phi of E minus phi of P divided by delta x. Okay. So here what we have, so we need to add actually. So what do we have? So let's say gamma of P, gamma of P plus gamma of W by 2 into A into phi P minus phi W by delta x. Let's say, what is this delta x? So we have seen that is between delta x pw. So this pw should come here. Plus, next you have gamma of p plus gamma of e divided by 2 into a. So we have phi e minus phi p divided by delta x p e plus, if we take is equal to 0, there is nothing source term. So if we don't have source term, we'll just take equal to 0. So this is what we have. This is the general formulation for the diffusion term. Okay, so we have taken the source term. So when you take the source term, so what happens? So the source term s of phi into dv. So basically, this will be combination of the linear term. So let's say this is constant plus s of phi into phi. Okay, so this will be a constant term, and this is the varying term. Okay, so here it's a linear combination. Source term, people assume linear combination, or it's a quadratic combination, any combination they can assume. So it's a combination of the linear term and the non-linear term. So here what we have seen, so we have seen the finite volume formulation. So where we have seen first the convection term, we have seen the diffusion term, and this is called the source term. So in general, so we have given the index notation for the 1D element. Basically, this is 1D element. So P and whatever the neighboring element, we have W, west node, and here we call west node, here we call east node, here will be east node. The distance between this grid point P and the west node is this one. Distance between grid point P and east node is this one, okay, which is delta x PE. This is delta x PW. Fine. So with this, what happened actually? We are getting, so what are the values? What is the distance between at point P and W? Point P and E. Okay. Then what we have? So we have seen the Navier-Stokes equation general, which is having unsteady diffusion, convection, next source term equation. Further, we gave an assumption where we'll neglect the unsteady, we neglect the convection term, we neglect the, let's say, source, not source terms like a gravity term or the body force term, pressure gradient term. So simply we have the diffusion term and the source term. Fine. So phi, we have taken any property, gamma is a diffusion coefficient. So the volume integral is converted to surface integral. So with that, we have done the finite formulation in between west node and point P, east node and point P, and then we join together, and then we have obtained this formulation. Okay, so then this is the source term. Okay, so here this is the formulation of the source term. Okay, so this is the general formulation of the finite volume method, and so this finite volume formulations you can see for 1D. So you have this element. So if you take 2D, so the complexity will increase. 3D, it will still increase. Fine. So the next class we will see in detail about 1D 2D comparison and how it is different and how many number of complexity will come. And for 1D element, so we'll solve one example. So of the temperature distribution between the rod. So how do we apply boundary conditions? How do we solve the matrix? Let's say you take 4 or 3 elements. So how many equations will be generated? How do you solve those equations using finite volume method? And what should be the criteria to solve these things? We will see in detail in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.